Oh, hey there. How is everyone? Well, that is a pleasant surprise having you here come today. You know me, I'm Mohammed Samir. I'm going to teach you SET physics. This lesson is called, well, oh, okay, whatever. I allow. Okay. Oh, I pressed the link. So I'm going to return back. Bye bye. Okay. Let's continue. So Isaac Newton, first, this lesson is really interesting. It's gravitational constants. And so a great deal of questions on the SET physics test is going to deal with gravity. So it's better for you to be well equipped for these kinds of problems. So let's move on to gravitational force. You know, any two masses attract each other in the universe, like any two masses. So this mass and that mass, you know, me and the computer monitor, there is a force of attraction between us. You know, any two forces that exist, they want to collide. But the reason we don't collide is because these forces are very small, and the magnitude of these forces that want big masses to attract each other depends on the mass. That is why when you jump, there is gravity. That is why there is gravity that actually pulls you down once you jump, because the Earth has a great mass that is going to actually create um, that force of attraction. So the rule, the rule is force of gravity is equal to G, and G essentially is gravitational constant. Okay, it's a number 6.67 times 10 power negative 11 meter cube per kilogram second squared. And you should memorize this number. It's important. 6.67 times 10 power negative 11 meters. 11. It's really important. And then you're going to multiply that. And here you have in this fraction, in the top part, is the product of the masses m1, m2, and at the bottom r squared. And r notates the distance between these two objects. And so if you have two planets, for example, and you want to calculate the force of attraction between these two planets, you'll bring the gravitational constant, you'll bring mass of planet m1 and the mass of planet m2. You'll multiply these together, put them up in the numerator, divide them by the square of the distance, and that is how you have the force of attraction between these two planets. Okay, well, hopefully that makes sense. So let's here see an example. And these problems, this kind of problem always comes on the test because the SAT not only wants you to memorize the rule, but it also wants you to plug in random variables and numbers and understand the behavior of everything. So calculate the resulting force of gravitational attraction between two masses if one of the masses was to double and the distance was to triple. So you go here in M1 or M2, and instead you say 2M1 or 2M2. And in the R, you remove the R and you put a bracket and you put 3R. So you will say G 2M1 M2, and you remove R and you put bracket 3R because he said triple 3R squared. So that is going to end up with G uh, 2M1 M2 divided by, well, 3 power 2 is 9, so that is 9R squared. And so what you realize is this is the factor of increase. It's 2 over 9. So the new gravitational attraction force is going to be 2 ninth the old gravitational force. So this is Gi and this is Gf. Gi, Gf is equal to 2/9 of Gi. So here we have this example. The final gravitational force is equal to 2/9. Okay. So the gravitational field is a vector quantity. It points downward towards Earth, and as you see, we're going to work on this equation right over here. That's very important. This is one thing you must memorize. Velocity of the orbit is equal to gm over r, and so we have planet that actually is. So I want to change the color. The planet, and around this planet there is an orbit. Okay, and so the satellite is rotating around Earth. There has to be a minimum velocity for this satellite to keep rotating around Earth or whatever planet it is for two things. First, not to fall down to Earth, and second, not to veer away from Earth. So that velocity is equal to root gm over r. What is gm? G is gravitational constant, 6.67 times 10 power negative 11, and m is the mass of the planet, not the mass of the satellite. It's the mass of the planet divided by the radius of orbit. Okay. So it now becomes apparent. Yes. So now we find the gravitational force can be calculated by two ways. You can either go this way or you can go that way. So the force due to gravity, you're probably familiar with this form. F equals mg. You know that. F equals mg is pretty straightforward. The force due to gravity is equal to the mass of the object times the acceleration due to gravity. So in the SAT physics program, it's considered to be 10 meters a second squared. And so you can say, all right, an object has 2 kilograms. The force due to gravity is 20 newtons. And you know this. This is new. Like here you have the satellite mass, and here you have the mass of the Earth, and you do that r squared. Here you bring the force of attraction of an object, not just a satellite, any object and Earth, no matter where that object is. Okay. So what the book is doing here, it's going to equalize mg with this form, and so the m's will cancel out, and so we have acceleration due to gravity equals gravitational constant, mass of the Earth over the radius of the Earth. And if you get the numbers from the internet and you factor these in, you put the mass and you put the squared radius of Earth, you will end up with 9.8 something. So, you know, the fact that the acceleration due to gravity is 9.8 actually scientifically and mathematically checks out. Now, if you see a question regarding the gravity of a planet, you know, the gravity of Earth is known, but the gravity of a planet talks about gravity means the acceleration due to gravity. Okay, so the acceleration due to gravity is going to be g m over r squared. That is the acceleration due to gravity. If you put that and factor it into Earth, that would be 9.8. Calculate the surface gravity of the moon. So that means the acceleration due to gravity, which we know right by now is going to be gm r squared. So surface gravity of the moon has mass. Put the mass, okay, and put the radius of the moon. Now, the reason we're putting the radius of the moon is important. I forgot to say this. The r is not exactly the distance between the two objects. It's the distance between the centers. So we have an object right here. this planet A and planet B. So r is the distance between the centers. Okay. So an object that is on the surface, and you just bring the radius of the planet in itself. Okay. So we will bring the numbers and put them here so that the gravitational constant of the moon is 1.62 meters a second squared. So now remember that during the circular motion, the acceleration, the centripetal acceleration is equal to v squared divided by r. We actually talked about this, and centripetal force is equal to mv squared divided by r. But if you're talking about an object, a satellite that is rotating, the acceleration, the centripetal acceleration is uh, the acceleration gm over r squared. It's the same thing as the gravitational acceleration on the planet. So you could substitute A of c with g of c. And so, for example, on Earth, let's say on Earth, you have a satellite that is rotating. So remove A of c and put 9.8 meters a second squared, and you'll have the radius of orbit and v squared. And so you will simply, very simply, uh, say, well, v squared equals gr. We substituted A of c with the g. Okay, so that's where it comes from. V squared equals gr, and so v will equal to the root gr. This is an r, really weird one. Okay, but this only exists if the orbiting satellite is near the surface of the planet. And so, if it's far away, if it's in a great distance, we're going to use gm over r. That is normal. And so, if you can, just always use this formula instead. This formula right over here is a lifesaver, like root gm over r. But if you're not given the mass, you can always use this formula as well. So calculate the speed of an orbiting satellite around Mars at a height of 3.57 meters above the center of the planet and the mass. So in this instance, you're always going to use root gm over r. Okay. So what will they do? I don't know what they'll do. Yes, the book did exactly as the formula we have taken says. But on the SAT, excuse me, on the SAT, you're not going to be calculated. You're not going to be calculating big numbers. You're going to be calculating small stuff. So you'll never use that. No, it'll never come to that. Okay. So these are important. Here's an example. So this one is important. A satellite orbiting. Okay, trying to use my pen. A satellite orbiting at a speed of v and a radius of r above the center of a planet climbs to a radius of 2r. It's the satellite's new orbital speed, so gm over r, that's what we know. So we're going to remove r and put 2r, so it'll be gm dividing it by 2r. So how is the new orbital velocity going to compare to the old one? Well, we have 1 over 2 right over here. So the new is equal to the old orbit, except that it's multiplied by root 1 over 2. So that is how you're going to solve it. And if you look here, for example, that is exactly how you solve it. Kepler's laws are not very important in this lesson, except that the areas that are covered in the same period of time are equal. So this area here is equal to that area there. Thank you very much, everyone, for tuning in, and I really wish you a great time in the midst of the coronavirus situation that is creating lots of Have a great day. Goodbye.